So today in Algebra 2, we are going to start Chapter 3, and Chapter 3 has to do with equivalent form. So we're going to look at functions, and we're going to come up with more than one way or more than one form of being able to show that they are equivalent or the same thing. And so we know that our big overarching expectation, I guess, for like Algebra 2 is to be able to look at functions and be able to come up with graphs, be able to come up with tables, come up with equations, that type of thing, all those different forms of when it comes to a function. So Chapter 3, especially on this first little part, we're really going to focus on expressions. So algebraically, we want to be able to write equivalencies. So on problem 3-2, we're going to do 3-2 and 3-3 today. 3-3 has to do with these two people, Jill and Terrell, and they're looking back to Chapter 1. And in Chapter 1, we sat there and went through and built this box, right? We took a piece of cardboard and we made it into a box, like with no top on it. So ultimately, and we'll go through how they come up with the dimensions, but Jill came up with one expression. She came up with this as an expression to represent the volume of our box, and Terrell came up with this expression for the volume for the box. And we just want to sit there and see if these two are equivalent, and we want to do it algebraically. So ultimately, I love that word ultimately, don't I? So they started off with, let's say, like a piece of cardboard, and if you take a piece of cardboard and you cut out the corners and you little squares out of the corner, all the same exact size, you can then like fold it up on these little folds, and then you end up with a box that doesn't have a top on it. Probably got to add some tape onto the side to keep those together, right? So we need to talk about our dimensions, I guess we can do that. So when Jill came up with her expression, they actually started off with a piece of cardboard that was a 15 by 20. I'm going to write my 15 down here. So it was a 15 by 20. But on that 15 by 20, they ended up cutting out those little X's, or sorry, those little boxes so they could fold it up. So we don't know how much they cut off, and you could change how much you cut off as long as it's a perfect square. The bigger square you cut off, if I cut off a bigger square and I go to fold that up, I'm going to have higher sides. So that's our variable that can change, is how big of a square we're cutting off. So that's our variable. So we're going to cut off a square, and we know a square has the same sides. So like you're cutting off a little x, right? And that x just denotes whatever length it is that you're cutting off. And that's true on all of these, right? You're cutting off that same size off of all of them. Oops, wherever we want to put our x's. So now when it comes to our box, this length is no longer 15. It started off as 15, but we cut off this x and we cut off this x. So now the side of our box is now going to be 15 minus x and x, which is 2 x's. Okay? And the same is true like when it comes to the length of this one. It used to be 20, but we cut off x and we cut off x. So we now have, this side would now be 20 minus x. Oh, sorry, 2x. We cut off 2 x's, minus 2x. And then our height of our box is going to be our x, whatever it is that we cut off. So if we look at our box that we have, and we're actually trying to find the volume, we know that the volume equals length times width times height. Some people use depth instead of height, but either way. So we could say one of these is our length, one of these is our width, and then that x is our height. And that's where Jill came up with 15 minus 2x times 20 minus 2x times x. So we want to know if that's equivalent to Terrell's expression. So I'm going to start off, because these are binomials. Okay. Oh, why am I doing the highlighter? So we have a binomial times a monomial, technically. So when I look at these little guys, I see these as little factors, and there's two ways that you can multiply these out. You can use that distributive property to share with everybody, or we can use the area model. Sometimes we call it the box method, but I know that CPM refers to it as the area model because you're actually finding the area of that box that you created. So I'm going to start off with our little box. All right, it's going to be a 2 by 2, and I'm going to start with these two. Whoops, it looks like I got the X in there. I'm going to start off with these two factors, or those two binomials. So I'd have 15 minus 2x times 20 minus 2x. So we're just going to multiply those using that area model. So 15 times 20 is 300, minus 40x minus 30x, and then a positive 4x squared. All right, everybody good there? So when I combine these, I'm just going to write it in that standard form from highest degree to lowest degree, just for clerical purposes, right? So how many x squareds do I have? I have 4x squared. How many x's do I have? This is going to give me my x's. I have negative 70 x's, and then I have 300, right? So now I have a trinomial, and I'm just going to throw that in parentheses because when I go back up to my original problem, right, we took care of the 15 minus 2x and we took care of the 20 minus 2x, and we still got to multiply by our x. So depending on where you want to stick it, you can stick it in the front or put it at the end. I'm just going to put it out to the front, right? And then now I'm going to use that distributive property, and I'm going to share that x with all three of my terms. So now I have 4x to the third minus 70x squared plus 300x. So I'm going to go up and check and see what Terrell came up with, and Terrell came up with 4x to the third minus 70x squared plus 300x, which is the same thing that we came out with. So are these equivalent? Yes, they are equivalent. It's just two separate ways in order to write the problem. And then of course, Gary, it's always Gary had to show up. And Gary sat there and decided to join the conversation, and he kind of sat there and he goes, well, I kind of like what you're talking about, maybe, but I kind of came up with a little bit of a different expression, and I think it's equivalent as well. And you're like, well, you know what, Gary? We know how to check that out and test it out. So you guys are going to test it, right? And I'm going to kind of do the same exact thing. I'm going to start with these two binomials, and I'm going to put them into our little area model. And I'm going to have 15 minus, oh, I was going to do a different color, right? 15 minus 2x, and then 10 minus x. Hopefully that shows, there we go. So now I'm just going to go through and multiply these out. What am I going to get? 150 minus 20x minus 15x plus 2x squared. So then just keeping it in that standard form of highest degree to lowest degree, I'm going to have 2x squared minus, I have 35x's plus 150. And because I know that I still need to multiply by that 2x, I'm just going to throw this all in parentheses. And then I got to still multiply by 2x. I can either put it in the front of my trinomial, or I can put it at the end of my trinomial. I'm just going to put it at the beginning of it. So we got a 2x out front. And then now I'm just going to keep using my distributive property, right? Because sharing is caring. We love to share in math. We give to everybody. So I'm going to make sure that I share that 2x with all of my terms. So what am I going to have? I'm going to have 4x squared minus 70x plus 300x. So I'm going to go back and look, and here this was Gary. This one was Terrell. Oops, sorry, Terrell. I think he's 1L. Is he 1L or 2 L's? He is 2 L's, right? Terrell. And then we started off, when it came to our whole box method, was looking at how Jill sat there and set up her problem. So when we came through, here's 3 different representations of an equivalent expression. We can write it 3 different ways. So that's what our goal is to sit there and be able to come up with those different ways of being able to represent that same expression. So on 3.3, there was just a couple more examples of, they say they want you to find at least 3 equivalent expressions for this. So when I start these problems off, for A, I noticed that this part is squared, so I'm going to start by squaring that. We just have to be careful when it comes to squaring. Squaring means multiplying by itself. Every now and then I'll get a student that wants to tell me that x plus 3 squared, they just want to square, like take the square inside, I guess, and they get this x squared plus 9. And I'm going to change this baby to red. That is not, whoops, I guess we can leave it there. That is not true, right? When something is being squared, squared means it's being multiplied by itself. So in order to multiply that by itself, we have to make sure we're multiplying it by itself, right? So ultimately, I would be rewriting that as x plus 3 times x plus 3. It's being multiplied by itself. Excuse me, and I still have that negative 4. So again, depending on what you're comfortable with, you can use the distributive method to make sure you are distributing to everybody, or we can use that area model. And I'm just going to jump to the area model. Whoop, I can't go that far over. Give myself a little space. All right. I have 2 terms, so it's going to be 2, right? This is 2 terms, so it's going to be 2 spots. So then I have x plus 3 and x plus 3. So to do that area model, I'm going to have what? X squared plus 3x plus 3x plus 9. I want to combine my like terms, so I have x squared plus 6x plus 9. And then I can't forget about this negative 4 up here, so I'm going to add him at the end. Then I'm going to simplify this. So x squared plus 6x plus 5, right? So we started with this form, so there's one representation. Here's another representation of the same thing that is equivalent. So you need to come up with one more. Well, technically this one is as well. This one, if you just left it as that 9 minus 4, that is also an equivalent expression. But then I'm going to look at this guy and I'm going to sit there and be like, maybe I can factor it. So if I want to try and factor this guy to see if I can come up with another equivalent expression to get x squared, I'm going to have x and x. I'm going to multiply to get a positive. So it's either got to be a positive positive or a negative negative. This is telling me it's got to be a positive positive. So I got to multiply to get 5, and when I add them together I get 6. So I'm going to go with a positive 2 and a positive 3. So there's another way of representing all of this information. If you wanted to, you could even do this by completing the square, right, where we had you had x squared plus 6x plus, you're going to leave a little spot, plus 5. I'm going to run out of room. Happens when you're in a hurry sometimes, isn't it? So we had x squared plus 6x plus whatever our perfect, right, plus 5 minus whatever our term is. So 6. Right, to figure out our term, it's going to be 6 divided by 2. And we're going to square that, which is 9. So a plus 9 and then a minus 9. So then our perfect square is going to end up being x plus 3 squared minus 4. So there's another representation for our equivalent expression. Right? They just kind of gave you guys a couple different problems. Like on this one, for b, we have to use our power property. So if we have 2a squared b to the third, right? A couple different ways you can think of this. This is to the third, so this is multiplying everything. You're multiplying it by itself 3 times, right? So this is technically 2a squared b to the third times 2a squared b to the third times 2a squared b to the third, right? These are the ones, because these are not polynomials, this is all like one term, you can then take that 3 all the way to all of this, right? So you can distribute to everybody. So this would be 2 to the third, which would be the same thing as 2 times 2 times 2, right? 2 to the third is 8, yep. You can go a squared times a squared times a squared is a to the 6th, where we know that we have to multiply our exponents. So we have a to the 6th. Then b to the third times b to the third times b to the third is b to the 9th, or we know that we can multiply those exponents and get b to the 9th. So here's an example of an equivalent form. You can even break this apart in a sense. You could say this was 8. I don't know, what do you want? A to the third times a to the third, b to the 8th times another b. You can kind of come up with a whole bunch of different scenarios or equivalent expressions for that one. And they really just have you guys going through and making sure that you remember some of your math properties. So on this one, this is the product property. Product is multiplying. So you have m squared n to the 5th times m n to the 4th. If you want to, you can put a 1 there if that makes you warm and fuzzy inside. So first thing I always do on these is I try to combine them or simplify them as much as possible before, before trying to come up with those separate equivalent forms. So this is m squared times m to the 1st. Oops, sorry about that. So that's going to give me m to the 3rd. Then I got n to the 5th and n to the 4th. So how many n's do I have? I got 5 of them and I got 4 of them. So I have a total of 9 of them. Right. And then they want you to come up with 3 other equations on those, so you can just break it down however you want. Right. You could even go m n to the 3rd and then take that whole thing to the 3rd, right? Because you would be multiplying through. So that would give you m to the 3rd, and this would give you n to the 9th. So I'm going to let you guys kind of play around with some different ones of those that you would like to end up coming up with. When they give it to you guys, when there's some fractions, on the first thing I would do on this one, when I look at my numerator, the part on the top, I have those 2 factors, or those 2 binomials. I'm going to multiply those 2 binomials together. So this time, instead of doing the box method, I'm just going to go ahead and do distribution, or some people call it the FOIL method, where I'm sharing with everybody. So x times 2x is going to give me 2x squared minus x plus 2x minus 1. And I'm just going to keep it going over x plus 2. Whoops. So I can simplify the top. I would have 2x squared plus x minus 1 all over x plus 2. So there's an example of an equivalent form, leaving it that way. You could go through and then factor the top and see if there's common factors on top and bottom that might cancel out for you, right? You could go through and multiply everything by 5, even if you started off with that original. So the original was x plus 1 times 2x minus 1 all over x plus 2. You could multiply the top and the bottom. I can multiply the top and the bottom by 5. So just for simplicity purposes, I'd put the 5 out front. X plus 1 times 2x minus 1 all over 5. And then I'm going to keep it in parentheses, that x plus 2. And did I change the problem at all? Absolutely not. Because like technically, those x plus 5 over 5 is 1. So I'm multiplying by 1, so I'm not changing the problem at all. Your guys' homework for today is kind of along that same lines. The assignment is just looking at some different equations and coming up with some equivalent forms. So I'm here all hour for you. Either like unmute your microphone and yell at me, or send me a message on chat, and I'll help you guys out.